In the last video, we completed quite a complicated optimization problem, and towards the end of the video, I had a set of students that were coming into my classroom, so I muted the microphone and finished making some notes at the very end here. What I hoped that you had picked up from that was that in the second derivative, we used the quotient rule to compute the second derivative, but I didn't bother simplifying it. I ended up using a scientific calculator. I don't want you to use a graphing calculator for these questions because I want you to be able to compute the calculus without reference to a visual aid. But I used a scientific calculator and I substituted the computed x value, the expected x value that would solve this problem, this 6.8399. I substituted that into this green calculation and it ended up being a positive 8.6784, which is positive. It's a greater than zero value. It's a positive value. So all of that work was to say that the second derivative at this position, at an x value of 6.8, is positive. And when the second derivative is positive, while the first derivative is equal to 0, we've got a position where we're concave up, and therefore a minimum value, which is what we were after. This x value minimizes the length of the ladder. Now the x value is the distance from the fence to the base of the ladder, not the ladder itself. So we had to use that x value inside our ladder length calculation. So a, the base there, is the x value plus 5, so that a value squared, and our b value is this resulting calculation, 8x plus 5 over x squared. And again, using a scientific calculator, we were able to determine that the ladder length, at a minimum, needs to be 18.2195 feet. Now, I don't know too many roofers or construction workers that are carrying around ladders are going to be performing calculus work here. But where this might be helpful is if you're in charge of a fleet of workers and you're sending them out to different jobs. A person's home might have these parameters, and you, as the person that's in charge of the logistics, might have to decide, are you sending out a truck with ladders on the rack, or are you going to have to send out a larger piece of equipment with maybe a boom lift in order to reach this house? Because clearly the cost of sending a truck with a ladder as opposed to renting a piece of equipment or sending your equipment such as a boom lift is radically different. And so by understanding this type of problem and being able to interpret it, we can see applications in the real world, even if the homeowner or the construction worker himself or herself don't necessarily do the work themselves. It is important to recognize its use and value. Now, for the next example in this lesson, we're going to talk about a more theoretical concept or problem. It's not really related to the real world as it sits right now. But when we're talking about, say, CAD designed models or shapes and objects or other machined parts, the computer is often going to interpret situations like this while describing the path of tools that are being used to make a particular part. And rather than dealing with an error on the computer side of things, sometimes it's easier to compute your expected results or verify your expected results before you punch in the requirements into the machine. So here we go with this particular example. A rectangle is constructed with its base on the x-axis and two of its vertices on the parabola y equals 16 minus x squared. What are the dimensions of the rectangle with the maximum area, and what is that area? Okay, so I'm going to just draw a picture here first. We've got an xy axis, and we're stating that the equation 16 minus x squared, now I'm going to have to adjust my scale here. 16 is our y-intercept. I'm going to place that right here. I'm going to call this 16, then therefore that's 8, and so on. So 16 is our y-intercept, and negative x squared, this is a downward-facing parabola. And I don't really need to draw this precisely, but what I'm going to do is I'm going to try to make this parabola strike here and here. And we'll just try to recreate this sketch the best we can. Well, that's not great, but I think it'll do for now. So the problem that we're faced is is this one. We've got a rectangle whose base is along the x-axis. And, here's a base that's along the x-axis, and then two of its vertices are now constrained, for lack of a better word, by the equation, 16 minus x squared. And this particular rectangle has a volume to it. I'm sorry, an area associated with it. And we can calculate the area, length times height. Now that shape has one area, but if I were to draw a rectangle in this shape, well, it might have a different area. Or if I were to draw a rectangle in this shape or this position, it too would have a different area. And the question becomes, rather than guessing and checking, can we find the precise dimensions for the rectangle that has the largest area based on these constraints or limitations? And I think we can. So I'm going to say that our objective is to find the maximum area, and area in this case is found by length times width. After all, we are dealing with a rectangle here. Now our constraints come into play, and they limit what values we can use for length and width. So our constraints are going to be something like this. Let's say that this measurement along the bottom is the width, and this measurement vertically is our length. Whether it's longer or shorter, it doesn't really make a difference, but we'll call those length and width. What we're going to recognize is that the width of the rectangle is closely related to the x value, or the x coordinate of this vertex. And so if x is the measurement here, then x, or negative x, is the measurement over here. When we're talking about the width itself, the width of the rectangle, that's simply 2 times x. Now, the length of the rectangle, well, that's closely related to this coordinate as well. And the length of the rectangle is going to be equivalent to the y coordinate. We were also told that the y coordinate is dependent upon this function, 16 minus x squared, so y is the same as 16 minus x squared. And I prefer this equation and this equation because now I can rewrite my objective in terms of a single variable, in this case the letter x. So our area formula very easily could be written as 16 minus x squared times 2x, because that is our length and width multiplied together. And if we're looking for the maximum area, then we need to find the derivative of this function. And certainly we can find the derivative now using the product rule, but this isn't too bad, so I'll probably just multiply these two together and use a series of power rules. So here's our area function, and what's really nice about this function too is that I can now calculate the area of the function without knowing the length and the width of the rectangle. If I want to know the area associated at this spot, all I have to do is find that x value and plug it into this equation. If I want the area at this spot, or any one of these positions along the way, all I have to do is plug it into this equation. In fact, at this point, since we have the area function written in terms of one letter, we could actually write this function this way, a of x. And that's really clearly stating that the area is dependent only on one measurement, the x value. The other measurements necessary to calculate the area of a rectangle have already been incorporated into this function. And that's pretty nice. That also allows me to use Lagrange notation when writing my derivatives, and I'm personally more comfortable with that. So our derivative is 32 minus 6x squared. And in order to find a critical point where our maximum or minimum occurs, we'll set this derivative equal to 0 and then solve for x. And so it appears that our optimal position is to let our x value be the square root of 32 over 6. And of course you could reduce that to 16 over 3, and that would be fine too. Positive or negative would work because, well, the position positive x or negative x is going to create the same rectangle. So whether you include or exclude these two, or one of these values, it really doesn't make a difference in this particular problem. So we think we found a solution, but we do need to verify that. So what I'm going to do next is find the second derivative. So I'll just jump off to the right side here. If a prime is 32 minus 6x squared, then a double prime is equal to negative 12x. And if I evaluate a double prime at the square root of 32 over 6, got to be careful here with my notation, 32 over 6, that entire fraction is inside the square root. I really need to make that clear. Well, that's going to be a negative 12 times something, some positive number, and a negative 12 times a positive number is going to be greater than 0. I'm sorry, less than 0, which is good, because when the first derivative is equal to 0 and the second derivative is less than 0, then we have found a maximum. Now, there was a second position, and this is what I was kind of hesitating about just a moment ago. If I evaluate a double prime at negative square root of 32 over 6, so negative square root 32 over 6, that produces a negative 12 times a negative number, which ends up being positive, and that indicates a minimum value. Well, that's kind of interesting, because we just said a second ago that whether x was positive or negative, we should create the same rectangle. But I think this negative x value is kind of producing a theoretical or hypothetical result. Now, off screen, I calculated the area based on the square root of 32 over 6, and that area ended up being a positive 49.2672, and when I evaluated the area at negative radical 32 over 6, that ended up calculating out to be negative 49.2672. So I didn't anticipate that type of result, but I suppose using our understanding of integral calculus, which we'll see in Unit 5, that starts to make a little bit of sense. Generally, when we're establishing an area underneath a curve and we're measuring rightward, we consider this area to be positive. And if we were to measure moving leftward, we generally consider that area, or accumulation, we call it, negative. And so I think that maybe that has something to do with these calculated results. But evidently, the maximum and the minimum points of this particular cubic function are identified at radical 32 over 6 and negative radical 32 over 6. It just turns out that the maximum area is calculated at this position. When we physically describe the resulting rectangle, however, it will also strike the x value at that negative radical 32 over 6. So, just to close this out, I know I wasn't real clear here, but I did take the x value that we solved for here at the first derivative and checked in our second derivative, and I'm applying that to the original area function, which is, let's go ahead and write it this way, radical 32 over 6, and so 32 times radical 32 over 6 minus 2 times radical 32 over 6 cubed ended up equaling 49.2672 square units. Let's try another example. And in order to stay consistent with the objectives of this portion of the class, we'll go ahead and skip Part B and C. I think those would be good challenge questions a little bit later in the course if we have time. But we've got squares with a side length x are cut out of each corner of a rectangular flat piece of cardboard, and that cardboard is 3 feet by 4 feet. The resulting piece of cardboard is then folded into a box without a lid. Find the volume of the largest box that can be formed this way. So here we go with our objective function. We need to find the volume of the largest box. The phrase largest leads me towards my objective. It looks like our constraints are that the cardboard itself is only 3 feet by 4 feet to begin with. Of course, if we had a 300-foot by 400-foot piece of cardboard, we can create a very large box, but if we're limited to 3 feet by 4 feet, then we've got a problem. And so if we're thinking about the scenario here, here's a box that's 3 feet by 4 feet. We're going to come in and cut corners out of this box. And those corners are square. And what we don't know is the dimension of each of those corners that's going to maximize the volume. But hopefully you can imagine that if I were to cut the corners out of this particular box, then this rectangle becomes the base, and with the base and the sides folded up, we'd end up with a rectangle that looks a rectangular box that looks something like this. It's got an open top to it, and the base ends up being, well, the result of the side lengths that are left over. So I think with our objective function, a good place to start is recognizing what the volume of a box would be. Now, the volume of a box, rectangular box, is length times width times height. And in our case, I think the length of the box would be measured, let's say, here. The width of the box is going to be measured here. So after the corners are cut and folded up, this measurement becomes the length. This measurement becomes the width. And it's this x value that becomes the height, because these two edges are going to be folded together to make this vertical box. Again, here's the front face, the sides, and the back. So x ended up getting folded up. We've got a length and a width to that particular box. And so our constraints then can be evaluated based on the cardboard being 3 units in one direction and 4 in the other. I think they did say feet, so 3 feet by 4 feet. And so our constraints here, remember, we're identifying our constraints in order to rewrite the objective function, and ideally our objective function will be written with a single variable. So let's see if we can do that. Can we rewrite L in terms of x? Well, certainly. If 4 is the entire width of the cardboard, and we cut off x units from each side of that, then this length down here would be the 4 feet originally minus 2 times whatever x ends up being. So 2 times x. So we'll say that length is equal to 4 minus 2x. We could say that the width is equal to 3 minus 2x with the same argument. And the height of the box is going to end up being just simply x. Now hopefully you're visualizing the problem here, or the situation. We could cut very small corners out of this larger sheet of cardboard, and with very small corners we end up getting a bit of a longer and wider box, but it ends up being very short, and we don't know how much volume this thing can hold in that situation. If our x values are relatively large, we might have a taller box, but it ends up being much narrower. And will the tall and narrow box give us more volume than the wide but short box? And this objective formula should allow us to see the answer. We'll replace L, W, and H with the constraint functions, because those are all written in terms of x. And then we should be able to find the derivative of the result. 4 minus 2x, 3 minus 2x, and x. Again, I think it's worthwhile to combine these by foiling and distributing, so I'm going to take a moment to do that off screen, and I would encourage you to do the same. And now that we have the volume formula based on x, the dimension of the corners that we cut from the original shape, we can compute the derivative of the volume formula. I'm a little bit nervous about this result. There is a common factor, but it's only 4, and that leaves us with 3 minus 7x plus 3x squared. And I'm trying to imagine when this expression is going to equal 0, and I'm afraid that this is not factorable. This non-standard trinomial doesn't have factors to it. So in order to solve this, now we don't really need to worry about this 4 since that's a scalar multiplier. We really just need to worry about these 3 coefficients, a, b, and c. I've got to go backwards here because the a value is always associated with x squared. But with an a value of 3, a b value of -7, and a c value of 3, we can use the quadratic formula to find the zeros of this guy. So I'm going to do that now off screen. And after using the quadratic formula, I see that the solution is going to be approximately 1.7676 and 0.5657. Now again, these are positions where the first derivative is equal to 0. We don't know if that's a maximum point or a minimum point. But if we look carefully, one of these won't make sense for this particular situation. Can you tell which one's not going to be any good? If you don't recognize it, that's okay. We can continue our analysis without that. Let's go ahead and talk about v double prime, because what we have to do next is verify whether these positions that produce a first derivative that's equal to 0, if at those positions we have a positive second derivative, then we know we've reached a minimum. If we have a negative second derivative, then we know we've reached a maximum point. So our second derivative, I'm looking at this guy up here, appears to be -28 plus 24x. And if we evaluate v double prime at 1.7676, I don't have to do all of the math here. I'm pretty well convinced that 24 times 1.7676, that's going to be a number bigger than 28. And so when we have -28 plus a number larger than 28, I know that my result is going to end up being greater than 0. And therefore, a positive second derivative when the first derivative is 0 indicates a minimum. So that's no good. V double prime at 0.5657, and here again I don't think I'll have to do the math completely. That would be -28 plus 24 times about a half, 0.5657. Well, I think 24 times a half is less than 28, so -28 plus that number, which is less than 28, is still going to remain less than 0. Therefore, we found a maximum. When the first derivative is 0, but our second derivative is negative, that means we're concave down at that position, and we've reached a maximum point. By the way, this 1.76 answer could have been thrown out if we had considered our domain restrictions, because imagine what would happen if I tried cutting a corner out of this box that was 1.7 inches long. Well, the width of this sheet of, feet, 1.7 feet long. If I had a sheet of cardboard that was only 3 feet wide and I tried cutting 1.7 feet from this side and then 1.7 feet from this side, well, the two would overlap and we wouldn't be able to create that box after all. So there's a benefit for considering our domain restrictions before doing all of that work. We could have saved a little bit of that analysis. Now there's one more example in this set of notes that I think we can cover. I think it would be worthwhile to set this one up and then let you work on your own. I'm fairly certain you're going to see questions like this in Math Excel, so you can probably learn a lot from their help tools, but I'll at least offer my commentary here as well. We've got this island out in the middle of an ocean that's 3.5 miles away from a straight shoreline. Cable needs to be run underwater from the island to this power station, and the question becomes, where should that cable divert from the shoreline to the island? Certainly if we measure 8 miles along the shore and then straight up to the island, that's going to be the longest path and potentially could be the most costly. If we were to lay this cable underwater from the power station straight to the island, that's the shortest path. But you'll notice that the cost to lay cable underwater is twice as much what it costs to lay cable on the ground or at the surface. And so it's assumed that there's a point somewhere in the middle that's X miles away from the power station. or more traditionally, it's X miles away from this perpendicular point along the shoreline. You could solve this in either way, but more traditionally we place the X value, the unknown here, in the triangle. Therefore, it would be 8 miles minus X distance away from the power station. The hints that I want to provide here is that since our objective is to minimize the cost of the project, this is something we really haven't seen much of before, but it's a good use of calculus here. Our objective is going to be to minimize the cost. And as a note, cost is equal to the rate that you're being charged times the quantity of items that you purchase. That's in general, rate times quantity, or price. Let's say it that way. That's more common. Price times quantity. So in this particular case, our cost is equal to some price along the shoreline, burying this cable in the shoreline based on price times some distance or length that's being buried on the shoreline, plus some different price in the water times our distance in the water. So our objective function really is a combination of two functions themselves, two price times quantity calculations. As far as our constraints go, what we know is that price 1, when we bury this along the ground, we'll call this distance 1 along the ground, and we'll call the distance in the water distance 2. So the price along the ground is $1,200, and the price along the water is $2,400. So that helps us a little bit with our constraints and rewriting our objective functions. There's no variables in those prices. But our distances, on the other hand, well, D1 along the shoreline is simply 8 minus X miles, and D2, the distance along the, or in the water, would be the result of another Pythagorean equation. And we've seen this before. X squared plus 3.5 squared, and the square root of that. X squared plus 3.5 squared. And so I would argue with these constraints known, we can now rewrite our cost function as the combination of a single variable instead of two different p-values and two different d-values. So the cost appears to me to be 1,200 times 8 minus x plus 2,400 times the square root of x squared plus 3.5 squared. And from here, I would think that it's off to the races for you. We can calculate the derivative of our objective function and set that equal to 0. If we need to use a scientific calculator to compute that result, that would be fine. And once we have our first derivative, we could calculate our second derivative and verify the points at which the first derivative are equal to 0 and determine when the second derivatives are positive and negative. Since we are trying to minimize cost, our objective is to minimize cost, we're hoping to find a point where the first derivative is 0 and the second derivative is positive. So I'm going to kind of stop talking here, and I'm going to let you work on this. So I'm going to ask that you pause the video, and I will put up a solution in just a moment so that you can check your work. Thanks for watching.